Okay, I think we can. So again, I'm going to encourage you to bring these with you to class on because I'm doing Friday and Monday for the next 2 class periods. Notes here. All right. So we should be able to do this kind of problem now where like at a certain location, the horizontal component of the Earth's magnetic field, horizontal meaning going this way, so you got the Earth's magnetic field going that way, is 2.5, oh, it's horizontal to the Earth. So it's due north at 2.5 times 10 to the negative 5 Teslas. We'll just kind of practice, And a proton moves eastward. Well, proton moving eastward with just the right speed for the magnetic force on it to balance its weight. Is that true? Is that what's going to happen? Yes, it is, because look what happens. If this is the uniform magnetic field and it's moving along this way, 90 degrees this way, velocity vector is going this way, magnetic field going that way, so it's going to go up. What's going into the page? If we're looking at this from the top, what's going into the page? You got it. Gravity, mg, is going into the page. So mg is equal to what? Right. We'll figure that out. QPB. And we know the mass of a proton. We know what g is. We know the charge of a proton. We know the magnetic field. We just need to find the velocity, how fast it needs to be going. So it stays right above the Earth's surface. That's kind of a fun problem. Now this one's a bit trickier. This one, I like this one because we have to think about it and talk about things. It says the drawing shows a parallel plate capacitor that is moving with a speed of 32 meters per second downward through a magnetic. Okay, so now notice the charges are going this way. They're making a 90-degree angle with it, right? Notice the velocity vector is perpendicular here. We've got to figure out how much the charge is. What is the magnetic force exerted on the positive plate? On the positive, notice they didn't say negative plate because it's going to be in the opposite direction. This thing might start flipping if you think about it. Because look what's happening. Magnetic field's is to the right. This is going down. So I've got a force that's going up. Is that correct? Right-hand rule says, no, I got a force that's going, so we got this, yeah. So I got a force, well, what's wrong here? Oh yeah, that was still the same. I just rotated that one, so that one still worked. Yeah, so I got a force going up. Notice there's a force going up on this one. So if I do the same thing with this guy, we got a force going. This thing could start, if we actually did this thing would start spinning because this has a force going into the page because it's the negative charges. So this thing would spin. It'd be a fun thing to see what the radius of it is and how much force it is. It'd be accelerating. What the mass? You can find the mass. You can find that it's period that it's spin. Whoa, we can just go nuts with this thing. But what do we have to do here? What do we have to do here? It's got it's got a E. The electric field is equal to 170 newtons per coulomb. I got to figure out what Q is. How the hell do I find Q? It's kind of a review. Parallel plate capacitor, what do we know? Well, okay, so it's a uniform electric field. All right. And each plate has an area. Aha! Each plate has an area of 7.5 times 10 to the negative 4 meters squared. That's going to tell me something. I think I can figure out Q from there. Gauss's law. It's going to look funny now, but we can do it. So about We'll do that. We'll start here in class. Okay. Now then, let's look at this mass spectrometer problem. Then I'll stop here for this page because we got 3 more pages of problems that we need to get set up here. But there's only like a handful of. I think there's only 3 pages, right? Yeah, there's 3 pages. So, all right. So, in an operating room, an anesthesiologist uses a mass spectrometers to monitor the respiratory gases of patients undergoing surgery. By the way, those of you who don't want to go all the way through medical school, we have a master's in anesthesiology here, where you become an anesthesiology tech person. You work for an anesthesiologist. You make good money. You don't have the insurance headaches. And we had the program here. But anyway, not through the physics department. We have one of our professors teaches over there. He loved it. But anyway, okay, in an operating room, this is just good old mass spectrometer stuff. We learned all about this. Here's the molecular mass of this thing. In a spectrometer, a singly ionized molecule of isoflurane, charged positive E, moves at a speed of 7.2 times 10 to the positive 3 on a circular path that is raised to 0.1 meters. What is the magnitude of the magnetic field? Well, I know this. I know that mv squared over r is equal to qvb. What are we looking for? We're looking for B. Nothing to that.